Hello, class. Welcome to our next lesson. Today we're going to spend another day in lesson 9.3, and we're going to discuss de Moivre's theorem. So this is a French name, a French mathematician. If you look at the first three letters of the word, for those of you who've taken French class, we know how to pronounce that as moi. So rather than moi, that's pronounced moi. So once again, I would call this de Moivre's theorem. And so what de Moivre's theorem says is that if we have a complex number in the form r times cosine theta plus I sine theta, or you might remember from the last lesson, we would often shorten this as r cis theta. And if it is a complex number, then if we raise z to the n power, the result will be r to the n power times the quantity cosine n times theta plus I sine n times theta. And for this to work, n has to be a positive integer. In simpler terms, if we use our cis notation, all we're saying is that z equals, if z equals r cis theta, if that's a complex number, then z to the n power, if we raise that complex number to any power, n, then that is equal to r to the n power times cis times n times theta. Let me briefly talk you through why this formula works. It's actually really one of the easier formulas to see why it works. We can prove it quite easily with the product equation that we learned in the previous lesson. And so let's take, let's say z equals r times cosine theta plus I sine theta, and let's raise it to the second power. So remember, when we're raising something to a power, we're multiplying by itself. And so z squared would mean z times z. And if z equals r times cosine theta plus I sine theta, that means we're going to have r times cosine theta plus I sine theta times another r times cosine theta times I sine theta. So then using our commutative property, we could bring the r's out front. So those become r squared. And then using yesterday's product equation, we talked about how if you multiply these together, yes, you bring those coefficients out front as a product. So that's where the r squared comes from. But also, you might remember that formula tells us that we add the angles. So we get cosine of the sum of the angles plus I sine the sum of those angles. So again, this is just the product formula that we looked at in the previous lesson. And then theta plus theta is 2 theta, both here and here. And so then that proves our formula. That's what we expected to get, right? Again, in simpler terms, if you wanted to look at it in cis notation, we would say z squared equals r squared times cis 2 theta. Okay, so whatever the power is, that becomes the new power for r. And then whatever that power is here becomes the coefficient that we multiply theta by when you're finding the cosine or I sine of that angle. Just to show you that this method continues, let's take it one step further. Let's say, what if I wanted to find z cubed? So if n were 3, then z cubed would be z squared times z. So what I can do is I can take what we just found for z squared and multiply it by z, which is r times cosine theta plus I sine theta. And then we can apply that product rule again. And so here's z squared. That's where we left off the last slide. Here's the original z we started with. So again, using that product formula, we can multiply the coefficients r squared and r. That gives us r cubed. And then we add the angles. So 2 theta plus theta becomes 3 theta, both here and here. And so z cubed equals r cubed times the quantity cosine 3 theta plus I sine 3 theta. Or if you are writing that in cis notation, it would just be r cubed cis 3 theta. And so we could continue that pattern for z to the fourth, z to the fifth, z to the sixth, and so on. You'll find that if you keep repeating that pattern, then the formula laid out before you works. And so here is that one more time. Here's in our cis notation. So again, what de Moivre's theorem says is that if we have a complex number in the form z equals r cis theta, if you raise that number to a power, all you have to do is take r to that power and then multiply the angle by that same power n. And so that's what we're going to do. That's going to be the first part of your homework assignment today, is they're going to give you a complex number that we raise to some power, and we're going to use de Moivre's theorem to give a simplified answer for that. Make sure you read the directions carefully. Notice how it's asking us to give an answer in a plus bi form. I apologize, the book kind of goes back and forth here. I think when I introduced this lesson to yesterday, or 2 days ago, I had x plus yi. So remember the x term is if we were graphing on a complex plane, x is how far we would go left and right, and y would be how far we would go up and down. And so for whatever reason, the book switches over today and they use a and b instead of x and y, which is okay. That's actually what most textbooks use, is a and b. So just know that a is your real number part and b is your complex number part, or your imaginary number part. The entire number itself is a complex number. So if we apply de Moivre's theorem, 4 is acting like our r value right now. So since we're taking this entire complex number to the third power, we'll say 4 to the third power. So 4 is our r value, n is 3 in this case. And then we're going to multiply that by cosine. And then we're going to take that angle 40 and we're going to multiply it by that exponent 3. So 3 times 40 degrees. And then same thing, plus I sine 3 times 40 degrees. And so then we're just going to do a little simplifying. So 4 cubed is 64. And then we want to go ahead and find, this will be 120 degrees. And so we want to go ahead and find those values. So here I'm going to go ahead and write that. I'll show one extra step here. So we're going to do cosine 120 plus I sine 120. Now you might be wondering, like, can I just write 64 cis 120 and be done? Well, it depends on the form that it asks for. So in this problem, they're asking for a plus bi form. And so right now it's not currently in that form. And so no, we don't want to just write 64 cis 120. In theory, we could give that as an answer, and that you could argue that that is an accurate answer for this problem. But I think it depends. Like anytime we do a math problem, we always want to read directions to see what kind of form they want it to be put in. And so in this case, in order to do this, we just need to substitute the value of cosine 120 and the value of sine 120 and then simplify. So that's what they're asking us to do here. So I'm going to go ahead and do that. So cosine 120 is -1/2. That's a value we should know from our unit circle. And then sine plus I sine 120. Don't forget your I. That'll be I. And then the sine of 120 is positive √3/2. And so then distribute your 64. So we end up with -32. The 2's cancel, and then the 2's cancel over here again. So plus 32 I √3. And now we can say that our answer is in the a plus bi form. So our a value would be -32, and our b value would be 32 √3. And so here we can stop. And this is the answer we're looking for. So the next problem is asking for the same thing. Let's just go ahead and answer it. Sorry, I was thinking about the next problem. But this one is actually very similar to the one before, so we'll just go through this one maybe a little bit quicker. So we're raising to the 5th power, so our R value is 2. This problem is already in polar form, and so we just want to apply de Moivre's theorem and then make sure the answer is in this a plus bi form. So we'll take R to the 5th power, and then we'll do cosine. Let me do brackets here. Cosine, and then we're going to take the angle given and multiply that by 5. So 5 times pi over 10. And then plus I sine the same thing. 5 times pi over 10. All right, so then just like the last problem, it's just a matter of substituting and simplifying. So 2 to the 5th is 32. And then 5 times pi over 10 will be pi over 2. So we'll say cosine pi over 2 plus I sine pi over 2. So pi over 2 are pretty friendly value that we know the sine and cosine of from our unit circle. So the next thing we'll do is just substitute those in. So cosine pi over 2, that's at 90 degrees, so that's 0. And then sine of pi over 2 is 1, so we'll be left with I guess if you want to write the 1, you can, I times 1. And then distribute, so 32 times 0 is 0. And 32 times I is 32I. So if you want to leave your answer this way, you can. 0 would be the real number part. So that means if you were graphing this, you wouldn't go left or right along the x-axis or the real number axis. And then you would go up 32 along the imaginary axis. So if you want to, you can also express this as just 32I. I suppose that would be considered most simplified. So the next problem you'll notice looks a little bit different. So you'll start your homework and I think you'll kind of get going and find this to be relatively easy. You'll be swimming along nicely. And then all of a sudden you're going to hit a problem like this and you're going to say, oh, wait a minute, the directions are the same. It says write each expression in standard form, a plus bi. But this problem looks a little bit different than this one. Notice this one has sine and cosine in it. This one does not. And so the difference is this problem here is already in polar form. And the next problem that we're given is not in polar form. And so I'll let you take a guess at what that means we need to do. Is, I guess, if we know how to do a problem, if it's in polar form, why not let's just change it to polar form? And so that's what we're going to do. Is we're going to just change this number to polar form because we already have a way of changing this to a plus bi form given that. So that'll be step 1. So this is just, if you have a problem like this, you're just going to have an extra step or maybe an extra couple steps because changing to polar form is a multi-step process. So let's see if we remember how to do this from the other day. First we need to find our R value. So remember, we can just use the Pythagorean theorem to help us out. If you need to draw a sketch to help you, you certainly can do that. So if I'm going over root 2 and down, so there's a 1 here, right? So over root 2 along my real axis and down 1. So that might put me about here. And so your reference triangle would be root 2 here, -1 here. So to find R is the hypotenuse, the distance traveled in that direction. So just use the Pythagorean theorem. So it would be the square root of root 2 squared plus -1 squared. So root 2 squared is 2, -1 squared is 1, so that just leaves me with the square root of 3. Okay, so we're halfway there. And then the other thing we want to do is find the the angle. So the angle at which we are traveling, root 3 units from the pole. And so to do that, again, there's a couple of ways. Sometimes you might be able to look at these values, X, Y, and R, say, oh, I recognize that. That's one of my common ratios, perhaps your 30, 60, 90, or your 45, 45, 90. If you can't tell what that is by looking at it, or maybe you just don't want to, like maybe it's just safer to use your calculator. Even if it is a common ratio and you don't recognize it or you don't care, you can always just use inverse tangent to help you out. And that might be the safe choice. I guess it could help you maybe prevent a mistake. So we're going to do inverse tangent, and then make sure we do y over x, so it'll be -1 over root 2. And I'm going to go ahead, this lesson is pretty much geared in degrees. I think later we're going to have a few examples where they talk about giving answers in degrees. And so I would recommend doing that for today. Set your calculator in degrees, and you should get something like -35.3 degrees. Is what I got. And then to be consistent with the book, I would encourage you, so -35 is the angle that you would get if you were to travel backwards from 0 degrees. But the way the book likes to express these answers is to let our angles be positive. So what they really want to know is, or what we want to know is, what is this angle? Let me try that again. Starting from 0 going forward. Okay, so if I want to give a positive angle here, all I need to do is add 360 degrees. And so I would encourage you to do that. I suppose you can argue, well, it's not technically wrong to say -35.3 degrees, but I think sometimes when we give answers, we like to be consistent and express things all in the same way. So I would recommend that if you want to be consistent with my answers that I'll give you, I would give positive answers for your angle. So just add 360, and that gives you about 324.7 degrees. Okay, so now that's just the setup. Now we're prepared to actually answer the question because now we have this problem. We can make it look like the other two problems. So now that we know our R value, if we go back to this problem here, now we just put our R value here, and then we'll have cosine and sine of that angle that we just found. So here's kind of our second part, is we'll take that R value that we just found, so √3. We're going to go √3, and then I guess we can go ahead, let's go ahead and apply de Moivre's theorem as we're writing this out. So, or maybe I could write it out here. So this would be √3 cis 324.7. And I know I have this written in cis form, and the examples we did previous had them written out long ways. So I'm going to write them out long ways on my next step. But here's the point in polar form. And so now that we have it in polar form, we'll go ahead and apply the theorem. So this time, go back to the original. We're taking to the 6th power. So we're going to do √3 to the 6th power. And then instead of writing cis, we're actually going to find the sine and cosine value. So I think it makes sense to go ahead and write them out long ways. So we're going to do cosine 6 times the angle that we found. So that was about 324.7 degrees. And then we're going to add I sine the same thing. So we'll do 6 times 324.7. All right, so at this point, you're probably going to need your calculator to help you out. So if you want to do this part first, √3 to the 6, so √3 times 3 will be 3, and then you have 3 pairs of those, so that would be, what, 27? So then we're going to have 27, all of this that we just had. And so if you want to multiply this and put an angle in here, you can, or if you want to just go ahead and do it all on your calculator. I think that's what I did. So I just went ahead and found the cosine of this product, and then I multiplied it by 27. And so that gave me negative 22.95. And then I did the same thing with the second part. I went ahead and found the sine of this product here, and then multiplied that by 27, and I got plus 14.23 I. And don't forget your I there. All right, so again, just to not lose sight of what we just did, what we've done is we've taken a number, a complex number, and we've raised it to a power. So that's what this resulting number is it's that original complex number that was given to us, root 2 minus I raised to the 6th power, and we've given our answer in the a plus bi form. Okay, so the second part of today's lesson is basically doing the opposite of what we just did. Okay, so what we just did was we found powers, so 3rd power, 4th power, 5th power of something. And so roots are the opposite of powers. And so if 3 to the 2nd power is 9, then the square root of 9 is 3. And so that's what we're going to be doing in the second part of the lesson is they're going to give you a complex number, and your job will be to find the square roots, the cubed roots, the fourth roots, and that will be given in the problem. And so here's kind of just some given information from the book on how to find it. It says, let W be a complex number and let N be greater than or equal to 2 be a positive integer. And it says that any complex number Z that satisfies the equation Z to the N equals W is a complex nth root. So basically all this is saying is that if you have a complex number, Z, and you raise it to some power N, and that gives you a new complex number W, then W is an nth root, or sorry, Z is a nth root of W. And so using that number with examples, so basically what we're saying is if the square root of 9 is 3, then 3 is a root of 9, a square root of 9. Okay, 3 is not a third root of 9, it's not a fourth root of 9, but it's a square root of 9. So if we said 3 cubed is 27, then we could say 3 is a cubed root of 27. And so to put this in terms that are a little bit more useful to you, here's the formula we're going to use. And so if W equals R cis theta of some angle is complex, then we're going to say that Z to the K equals square root, nth root of R times cis the angle plus 2 pi K over N. Or if you're using degrees, instead of 2 pi K, we'll use 360 degrees K. Okay, now this formula looks a little bit complicated, but once we actually use it, you'll kind of see what I mean by it's pretty much the opposite of what we were doing. So instead of taking R to the nth power, we're going to take the nth root of R, and instead of multiplying theta by N, we're going to divide by N. And so I think probably the best thing to do is just look at an example. So let's try one. So this says find all complex roots, leave your answer in polar form. So this is just the directions that the book will give you. And so this is probably the more important part. It says the complex cubed roots of 1 plus I. Okay, so they're giving us a problem in a plus bi form. So just like the last problem, for really every problem that you do in your homework today, you want to start with the number being in polar form. And so when you start your homework, sometimes it will be already in polar form for you. And so you'll like those. Those will be easy to get started with. And then as we noticed with our third example, if it's not in polar form, you need to change it to polar form. So when you get to the second half of the assignment, I think for all of these, you're going to recognize that these are not in polar form. And so just kind of keep that in the back of your mind for every single problem you do today. If the problem is not in polar form, change it to polar form first. Okay, so I'll make a little note of that here. So change to polar form. So I guess I just can't stress this enough. I think you can reduce a lot of confusion in today's homework if you just remember that for every single problem, start in polar form. So if it is in polar form already, great. If not, just change it to polar form. That's something we learned how to do in a previous lesson. So in this problem, we'll do that first. Let's find R. So again, if it helps to draw a little sketch, you certainly can do that. It's probably not required once you start to get good at these. So if I were to go over 1 and up 1, my point's going to be up here somewhere. So 1 and 1. And so R will just be 1 squared plus 1 squared, or the square root of that. And so R in this case will be the square root of 2. And then for our angle, this is one that you should recognize as 45 degrees. But keep in mind, you're always welcome to do the inverse tangent if you want to. You would just do inverse tangent 1 over 1, which is 45 degrees. And so if you need to use your inverse tangent button, you're welcome to, but sometimes you should be able to recognize what that angle is without any further work. All right, so this number in polar form is root 2 cis 45 degrees. So now that we have it in polar form, we should be prepared to answer this question. So remember, we're just doing the opposite of what we did before. Now, before we continue, this part of the question is really important. It says we're finding the complex cubed roots. So this word is really important because if it said 4th root, 5th root, square root, we would do the problem a little differently for each type. So with cubed root, that just means that if we go back to this formula, n is going to be 3. And so we're going to start by doing the cubed root of r. So since r is root 2, we're going to say the cubed root of root 2. And we'll clean that up here in a minute. We'll figure out how to simplify that. So then I'm going to go ahead and use my cis notation. So I'm going to say cis, and then if we go back to this formula, let's go with degrees. Since we wrote it, our angle is 45 degrees. So what we're going to do, this sub-0 here, this just means the first angle. So the first angle will be the one that you find as part of your work here. And then to find the following angles, what you're going to do is you're going to add 360 k over n. And so I'll show you what that looks like. Again, it looks kind of confusing, but it actually works out pretty nicely. So the first angle will just be the one that you found, so 45 degrees. And I'm going to call this z sub 0. Okay, z sub 0 is kind of like your original, your first at time 0, however you want to state that. That's the first one. And unlike the previous problems that we did, this isn't our final answer and we're done. Like when we did these, find the 6th power, find the 3rd power, there's one answer. But you know from mathematics that when I say the square root of 9, there's actually 2 square roots of 9, right? There's a 3 and there's a negative 3. Or when I say find the cubed root of something, there could be up to 3 roots of that. And so that's something you should keep in mind, is if you're finding the cubed root of a number, there should be 3 answers. If you're finding a 4th root of a number, there's going to be 4 answers. If you're finding a 5th root of a number, there's going to be 5 answers. So z sub 0 will be your first answer. And to clean this up just a little bit, maybe do you guys remember writing square roots like this, like 2 to the 1/2 power? So if we think of square root of 2 as 2 to the 1/2, and the cubed root of 3 as 2 to the 1/3, then if we have a power to a power, we multiply. So couldn't we call this 2 to the 6th power? And you could either write 2 to the 6th, or if you'd rather do like 6th root of 2 like that, you're welcome to do that. What I would not do on this problem is I would not just write some random rounded decimal value that you find on your calculator. I think we typically prefer exact answers. And so I would just recommend either 2 to the 1/6 or 6th root of 2. So we'll say cis 45. Now you're going to notice the book kind of gives you a gift here. If we go back to the directions, it says leave your answers in polar form. So that's great news for us. If you look at the previous 3 examples that we did first, those wanted in the a plus bi form. So for those, we had to find cosine and sine of the values and substitute and simplify. But for these, you do not have to do that. It says you can leave it in polar form, so our cis notation is our accepted polar form. And so this will be your first answer. And then to find the second one, all you're going to do is we're going to use the same R value, 6th root of 2, and then you're going to take your angle, 45, and you are going to add 1/3 of 360. Okay, so take that angle 45, whatever your starting angle is, and then you take 1 revolution and you just divide by n. So since we're finding the third root, we're going to divide by 3. And so to simplify that, we'll have the 6th root of 2 times cis. And so you take 45, you add 120, and so that puts us at 135. And so this will be our second root. I know it's called Z1, but it's how we label our second root. And so then we're ready to find our third and final root, Z2. And so we'll have 6th root of 2 once again. Once you find that front number, that is the same coefficient for all 3, 4, 5 of your answers. Okay, so then on this time, we're going to take the angle and whatever this angle was. So like this value is 120. And so all you're going to do is just add 120 to this angle again. And so if you take 135 and add 120, you get 255. And there's one thing you can do, like if you're ever kind of worried about whether your answer is correct or not, if you take this 120 that we just found and you add it to 255, it should take you back to 45. So if, for example, if we start with 255, it takes, what is that, 100? So if you take the 255 and you add 120, that takes you up to 375. And if you take 375 and subtract 360, that gives you 45. And so that's what I mean is it kind of recycles itself. It goes around 1 revolution, and then it should land back where that first angle landed. If that doesn't happen, that means you would have made a mistake at some point, and you might want to check those angles again carefully. And so whatever this angle you find here, you just keep adding it. So again, to get from here to here, I added 120 degrees. And to get from here to here, I added 120 degrees. And if I add 120 degrees, that gives you an angle that lands in the same place as 45 degrees. All right, so our final answer, if you're kind of unsure about what's my answer here, so here's one of my roots, and here's my second root, and here's my third root. And don't get too caught up on the names. Again, I'm just trying to be consistent with the textbook here. So they use sub-0 for your first root, sub-1 for your second root, sub-2 for your third root. And so just keep in mind that if you're finding the cubed root, you should have 3 answers and so on. So here I've got one more example. We should be able to go through this a little bit faster. So this one's asking for cubed roots again. So we should know that we'll have 3 answers once more. And so remember our same advice from before, always change to polar form first. So I believe all of the problems that they give you in the second half of the assignment will not be in polar form. So I would do that first. I'm going to go ahead and pause the video and do that just to save a little time. Okay, so I went ahead and found R. Again, just use the Pythagorean theorem. So 4 squared, negative 4 root 3 squared, you get 16 and 48. Square root of 64 is 8. So for R value. And then for theta, again, you can draw your triangle. Maybe it's an angle that you can find. 60 degrees actually is an angle that we could probably find with the ratios of that triangle. But I would argue that it's probably easier and maybe avoid mistakes if you just go ahead and use your inverse tangent button. So I put the y over x, and then I got negative 60. And remember, for this assignment, we like to give positive angle measures. So to make this positive, just add 360, 1 revolution, and we'll get 300 degrees. And so now we have our coordinate in polar form. We could say z equals 8 cis 300. So again, this is not our final answer. This is just our, now it's going to be our starting point for what we need to do next. And so we're finding the cubed root. Actually, I think I'm going to change that. Why don't we change this to fourth root, just to be different. I guess we already did a third root one. So here, let me change that for us. So let's find the complex fourth roots. That's what we're going to do. There we go. So that'll allow us to see an example with a different number for n. So let's go ahead and do that. So let's take our polar coordinate that we just found here. So this time we're going to take the r value 8, and we're going to take the fourth root of that. So again, this is, if it's a third root, this will be a 3. If it's fourth root, this will be 4. So we're going to do the fourth root of 8, and then we're going to do cis and take the angle that we found, 300, and divide that by 4. And so this will be your first root, z0, sub 0. And so then we could do a little bit of simplifying, I suppose. There's really not a great way to simplify fourth root of 8. If you multiply, or sorry, factor 8, you get 2 times 2 times 2. So you can't take any 2's out because you would need 4 of them in order to do that. So I would argue that we could just leave this as fourth root of 8. I think that would be fine. And then divide this, you should get cis 75. So that's going to be our first root. And then for the next one, again, that coefficient stays the same. And to find the next angle, just all you need to do is take 360, 1 revolution, and divide that by that same n value, 4. And so in this case, we get 90 degrees. And so that's the number that you add to 75 to get your next angle. And so this will be fourth root of 8 cis 165. And so that's our next root. Okay, so I went ahead and finished that up for us. So again, that front coefficient just stays the same, and to get each of the new angles, you just continue adding 90 over and over again. And you might say, well, how do I know when to stop? Well, if you're doing the fourth root, you should stop after the fourth one. But also, if you were to keep going and you took 345 and you added 90, that gives you 435. And if you subtract 360 from that, that takes you back to 75, which is where you started. So the next angle in line is going to be going to have the same coterminal angle as 75 degrees. And so that would be another reason to tell you to stop. Okay, so that's it. Here's your homework. You're going to go to page 609, start with 44, and work your way up through 60. And I cannot stress enough, let me just copy and paste this one more time, that for every problem that you do today, make sure you are converting to polar form first, okay? If it is not in polar form, you're going to look at your formulas and feel kind of confused and not sure what you're supposed to do. And so they kind of help you out as you get started with your homework. Again, those first few examples, they're already going to be in polar form. They won't be in cis notation. Your book doesn't use that cis notation. They'll have it written out like with the word cosine and sine. So remember, for those, just substitute, simplify, and you're done. And your answer will be in A plus BI form. And then eventually they'll switch over and they'll give you some that are in A plus BI form. And so you have to change it to polar form. And then when you're all done, it goes back to A plus BI form. And so it kind of feels a little redundant, but there's not really a good way to turn a number like this without foiling it out 6 times. And I don't think we want to do that. And so we can use our formula if we're willing to just change it to polar form first. So I would highly recommend that you do that, change to polar form. And then for all of these where you're finding the complex or nth roots, those need to be changed to polar form as well. I don't think any of those will already be in polar form. Okay, so That's my strongest advice for you with today's work, is to make sure that the number is in polar form before you apply either of those formulas. If you do that, then I think you're going to do great. So keep up the good work. Sorry for the long video. If you need anything at all, please let me know, and I'd be happy to help in any way that I can.